Welcome back. Well, I came upon this problem, well, I actually seen it a long time ago, where you've got some kind of nonlinearity in a system. It's a static nonlinearity. There's no dynamics in it at all. But you want to find out what that nonlinearity is. And so, there's a picture of a nonlinearity. So you might want to represent it as a polynomial. So there's x and y. So y is a0 plus a1x plus a2x squared and so on up to an x to the n. So this would be a straight line, for example. I'll be constant and then a straight line and then a quadratic and then cubic and so on, depending on the fit that you would want. But the question is, how would you even know what that is in the first place? Never mind even fitting a polynomial to it. So it struck me what you can actually do is a test. If you actually have access to the input, you can measure the output. You can do something similar to a frequency response. So over here we have the nonlinearity, and you put a sine wave in. It turns out the sine wave's got to be at a reasonably high frequency compared with the sampling rate. It's all done digitally, of course. Maybe a fifth of the sampling rate, something like that. Fs over 5. And so we generate data at the input and we collect the data at the output. So we've got y and x. This is getting into an area which is sometimes called data science nowadays. We're trying to fit models to nonlinearities and so on. But how could we identify what's in there? Well, the way we do it is we use the method of steepest descent or gradient descent, and we define an error which is the output, but here it's going to be time varying. I mean, this actually, the nonlinearity could be varying in time even. It doesn't have to be constant. It usually is constant, but it could be varying. And so we then define an error between the actual output and this thing here, which we define as V transpose W. That's a dot product of two vectors. W is going to have the components of all the coefficients, hopefully, if it works, A0, A1, A2 and so on. And V is this vector here, which is just values of x, which is this here. In this case it would be our signal that's going into the nonlinearity at a particular point in time. And statically it's just 1x, x squared and so on up to x to the n, or at each point in time it's 1x of k, x squared of k and so on up to x to the n of k. So that vector v is important. W will just be a vector of coefficients, so it's going to be like this, w0 up to wn. And hopefully if our algorithm works, this will contain all the coefficients of the polynomial. So we can do some maths. We're going to use the method of steepest descent, or the gradient method. We can work out the gradient of the error. This is a scalar quantity, although these are, W is a vector. And when we differentiate the scalar with respect to a vector, we get a vector which is called the gradient. And if we go in the negative direction of the gradient, we end up with this update here, which is wk plus 1, the new, at least the new estimate of the coefficients of the polynomial is the previous one, wk plus mu, which is a step size, times v, which we've already talked about, times the error, which we've already talked about. So we define the error and then we work out the update. This thing mu is a step size, and you don't want to make it too big, so I'll show you it will go unstable if you do that. Too small, it'll be very slow convergence. Now this algorithm might be familiar to many of you because it looks very similar to least mean squares if you've worked on adaptive filtering. In fact, it is very similar. The only difference is in least mean squares you're not identifying a static nonlinearity, you're identifying a dynamic system. And the x terms here would be xk minus 1, xk minus 2 and so on. They wouldn't be squared. But here they're squared and cubed and so on up to the nth power, which is quite interesting. So without more ado, let's see if it actually works. So what I've got here is a LabView program. I actually did this in MATLAB first, but I found that I didn't have the sort of artistry with MATLAB to do an animation, which looks much more impressive with this user interface that I do with LabView. So what I've got here is, here's the mu value. I can change that. That's the step size. And these are values of the polynomial, which can be up, in this case, up to 4th order, but I can keep adding as many as I like. But these are just so I can slide them and control the values. So a0, for example, could be 0 there, or -2, or I can just change these, do anything I like. And right up to the 4th order power. So there's 5 weights altogether. I can change the x-axis scaling and so on. And I'm just going to begin with have a straight line. So I'm just going to have 1 and 2 as the 2 parameters. So it's like y equals x plus 2x plus 1. So that's a straight line. So let's run it and see. And just to begin with, it's just going to draw it. And there's the blue line is actually the polynomial itself, which is a straight line, of course. I can change here the slope of it, make it negative, positive. I can do the same with the intercept. That's moving the y equals mx plus c, that's the c part. Leave it at 1 for the moment. And actually, if I turn the mu, the step size to 0, nothing happens. You see the red, this is the estimate, but it doesn't take much to actually get a brilliant, actually it's so quick there, it's actually converging to the, and it's right, sitting right on top. The red and the blue are right on top of one another. The estimates are here, and you see they're 1 and 2, sort of 0 error, because it's deterministic here. So let's make it a little bit more difficult, and we'll add some other terms. So there's quadratic term, and you'll see it changing. Well, let me show you changing. So there's a quadratic term, a cubic term, and a 4th term. So that's a 5th order polynomial. Looks a bit like a cubic, but it's not. It's 4th order. I'll have to change the number of weights now from 2 to 5. Otherwise, what it's trying to do now is fit a 2nd order, and you see it. Of course, it's trying to fit a straight line to that, which is not bad actually, but not much use. So let's increase it to 3rd order, and there it is. It's trying to fit a cubic to it now. Make it 4th order, and it's not bad. And then 5th order, and you'd think, oh wait a minute, that's 5th order, and it's still not got it. Well, that's because it actually I've made mu too small. When mu is too small, it doesn't converge. So although we don't see the time, we're not actually seeing time in that axis. It's just I haven't got enough data samples for it to converge. So I can make mu larger, and then you see the bottom. You see I'm actually increasing mu, and then you see how there we've got a perfect fit now. And I'm just increasing mu. And if we have a look at the weights there, you'll see they're 1, 2, 2.99, 2 again, and minus 0.99. So they should be 1, 2, 3, 2, and minus 1. Pretty damn good, actually. So there it is. Now we can increase the estimated number of weights beyond 5. So we're fitting like a 6th order polynomial. So there's 6 weights, for example, and you see it's mismatched now. We'll keep going. 7th order, 8th order, 9th order. There's a 9th order. And let's see what happens. Well, you see it's trying to do its best, isn't it? I'm just reducing the gain a little bit, and see you can see that it's not a bad fit there. And I can keep going in as many times, order I like. The 16th order estimate, and I'm just trying to fit to a 4th order. It's got a bad mismatch there. You can see the red line coming down there, and it's quite interesting to play with. And this is why I wanted the animation, for the very reason that I can see what's going on. So that's just me adjusting the step size. So this algorithm is very much like least mean squares. In fact, you could probably use recursive least squares as well, a little bit more complicated. So when I did the sums, and it was quite interesting that it came out that way. But it would be an interesting thing to try in real life. I might do it one day to actually estimate the real nonlinearity rather than just a simulation here. And but the method itself isn't particularly new. As I say, there are papers around this and more modern papers linking it to neural networks. But I thought I'd give it a try anyway. Okay, thank you very much. Bye-bye.